will be given by Robin Blume Kohout from Sandia National Labs, and he'll talk about characterizing multi-bit QIP's state of play. Thanks.
Thank you very much. In the immortal words of the Beatles, is this thing on? How about now? Wow. All right. So this is an absolute delight. I graduated, I got my PhD from Cal in some spring 2005, and I have been eagerly waiting ever since to see when my alma mater would invite me back to give a talk. As it turns out, the restraining order expires after 10 years, and here I am. So thank you very much, Irfan. Having complimented you for this wonderful workshop, I now want to question your judgment. Who thought it was a good idea to put a bunch of physicists in a room and have them sit through a whole day of cool, exciting science talks, and then put the engineering talks at the very end? So what I'm going to do here is I'm going to try to take a subject that at least half of you probably think is terribly boring, and I'm going to try to make it look interesting by giving a talk that's really fluffy, or at least the first half of it is going to be sort of fluff. But what I want to do is I want to convey a message, and then towards the end, when I've got you lulled into a sense of security, I'll actually buckle down and start throwing up really busy slides with math and words and things like that. But I want to start out by pointing out something that it's amazing how banal it is to say that small quantum computers are here. I've been working in this field for the better part of 20 years now. 20 years ago, I don't think most of us thought this day would come. That, I mean, hi, quantum computers, people, right? They don't maybe look like this. I like this picture a lot. I think this is probably me, the guy in the lab coat with tail. But now that we actually have small devices that do all of the things that a quantum computer does, or at least in the press materials, they are claimed to do all of the things that a quantum computer does, there are some really important questions that come up. One of them, obviously, one of the things we've been talking about today is, what do we do with it if it works? I want to step back. I want to ask, does it work? Will it work? How does it work? For that matter, what does it even mean for it to work? How do we know whether a piece of hardware that our favorite experimentalist dropped into our laps actually does work? If that hardware is a fully fledged small quantum information processor, or if that piece of hardware is just a single qubit, a single gate, a single interface that will be plugged together to make a quantum computer. Furthermore, one of the things we've been talking about today is, what would we do with a small quantum computer? So there's a variety of possibilities. The most exciting one, of course, we're all scientists, right? And so our first priority is money. So the most exciting thing is that we might be able to solve very hard problems, and by very hard problems, I mean problems that someone would pay us an enormous amount of money to solve. So this would be fantastic, but no. You're not going to do this with a small 10 or 20 qubit quantum computer. Hartmut pointed out yesterday we might be able to do this with a 49 qubit quantum computer, but actually the first demonstrations of quantum supremacy are not going to be worth a whole bunch of money. So moving on, we know that quantum error correction and logical qubits are going to be necessary for the future, so one of the other hopes is maybe we can learn something fundamental that we didn't know about how quantum error correction and fault tolerance work. But this is actually not the case either, because we can simulate devices of this size on a classical computer, and so it's extremely unlikely that we're going to learn anything deep about error correction and fault tolerance theory that we didn't already know. So I want to focus on the remaining two ideas. We will certainly learn a tremendous amount about engineering and integration by building these devices. But I think the single most important thing that will come out of Pathfinder test-bed quantum computers that we see over the next couple of years is learning how they don't work, learning about realistic noise and errors in quantum hardware. And this is what characterization means. It means doing experiments that teach you what real quantum computers are like today, and therefore what they're going to be like in the future, so that we can design error correction protocols that will make them useful and lead to, of course, lots and lots of money. There are an amazing variety right now and over the course of the next year of small quantum computers. Devices, some of them publicly accessible, with between 5 and 17 qubits in them. This is almost certainly an incomplete list, much like the word incomplete is incomplete. I apologize to those of you whose 5 to 17 qubit quantum computers I left off the list. I am just blown away by the fact that there's anything on this list. How exciting is this, seriously? And now we have Google threatening to drop 49 qubits on us next week, and 1 million apparently the month after that, and it's actually getting more than a little bit terrifying for me, because it's my job and my group's job to figure out how to test these things, how to benchmark them, how to characterize them, and preferably how to do so, before anybody tries to do something useful with them, so that we know how they're going to fail and how to fix it. And frankly, a word to the experimentalists in the room: stop it. You've gotten ahead, okay? Just go on a vacation, let me catch up. And since you're not going to do that, let me focus in briefly on one of those devices, arguably the one that has gotten the most press, the IBM Quantum Experience. And I think the reason that it's gotten so much press is because there's a fantastic photographer working for IBM. And I really like this photograph, not just because it's a really well-lit profile of Jake Gambetta, but because it juxtaposes two things that are critical elements and perspectives on near-term quantum computers. There's the hardware, the superconducting circuits that make up IBM's device, and there's the software, the quantum circuits that we use to describe what we're going to do with them. These quantum circuits are a language. In fact, they are pretty much the language for describing experiments that people will do on quantum computers. If you're an experimentalist, you might take issue with that. You might say, I describe my experiments in a different language, the language of physics. I do things involving units, for example, megahertz and meters. And I say, as long as you're talking about megahertz and meters, you're not treating your device as a quantum computer. You're treating your device as a physics experiment. The day that it becomes a quantum computer is the day that you start describing it in terms of quantum circuits. And so this is the yin and the yang of quantum computing in the age that we are moving into right now. The hardware and the software. And I want to make a couple of fluffy, pedantic points using this yin and yang symbol. The first is that characterizing hardware is a software application. Let me flip back briefly. If I want to understand how this works, I'm going to run circuits, because all the experiments that I'm going to do in the future on this device are going to be described by circuits. So one of the things that I will do with this device is characterize it. Those characterization protocols are described in terms of quantum circuits, and they should be. There should be no meters, no megahertz, no units, no physics in your characterization. Okay, there's physics in everything, right? We're physicists, many of us are, but the point is, this is now moving into quantum computer science. This is software. Characterizing hardware is a software application. And secondly, why characterize hardware? The reason to characterize the hardware is to know how software will run. So let me put these two yin-yangs together with homage here to IBM, because they like what's called the Smolin spiral as a descriptor of how characterization works. This is a different spiral. And I want to focus on the role that circuits play in it. We perform special circuits, quantum characterization, verification, and validation circuits. And the purpose of those circuits, when we perform those circuits as experiments on hardware, is to make inference about the properties of the hardware. And the reason that we make that inference, the reason that we go to all the effort to figure out how well the hardware works and how it fails, is because we want to make predictions about other circuits. Not these circuits, which is why this is a spiral, not a loop. These are different circuits. These are the ones that run Jared's quantum algorithms. These are the ones that run quantum error correction circuits. These are the circuits whose outcomes have money in them, or scientific utility, or something other than just learning about your hardware. So we start with circuits, and we end with circuits. Let me give you two examples of how you could implement this spiral. Example one, I could choose a bag full of many, many circuits chosen randomly from some ensemble of possible circuits. And I could take those circuits and I can run them on my hardware, and I can take the results of that, the data, and feed it into a mathematical machine, an algorithm. And I could infer from that the average over all those circuits of the failure rate of those random circuits. And then, given that number, I could make predictions about particular circuits that I care about. Say quantum error correction circuits, because that's what I tend to think about more than algorithms. I'm focused on first, build the logical qubits, then run the algorithms on them. So this is what keeps me up at night. How well will a QEC circuit perform? What's awkward about this is that this is not one of the circuits that I ran up here. I suppose it could be, if I got lucky. But I have a huge ensemble of circuits. If I choose at random, I probably am not going to run that circuit, the quantum error correction circuit. It's a particular circuit. It has particular structure to it. And one of the things that does keep me up at night is that if I only know the average of these circuits, I can't predict exactly what that circuit will do. I have to put in a lot of assumptions and approximations. And Joe Emerson talked about that yesterday in the discussion of different forms of randomized benchmarking and the challenges in taking the results of RB and using it to predict practical circuits. Another example, very similar diagram. I could choose many structured circuits. The reason I want to do that is that ultimately the circuits that I'm going to run, the algorithms, the quantum error correction codes, etc., those are going to have structure to them. They're not random. So if I choose the structured circuits and I run them and I feed them into a machine, a different machine, I could infer what the quantum process matrices, the noisy operations that describe each of these gates are. Because while this circuit is not one of the ones that I ran up here, these gates are the same ones that make up these circuits up here. And so I can infer something about these gates from the results of these experiments. And if I can do that, then I can predict the logical error rate, the failure probability of that circuit and any other circuit. And I can also predict a tremendous number of other things. I can predict the distribution of syndrome outcomes. I can predict how it will fail, not just how often it will fail. It gives me a tremendous amount of power. Sure. So what I'm arguing here is that you don't actually. That what you learn from random circuits is not powerful enough to predict specific circuits accurately. This is a fluff talk. So there is certainly a missing argument that I will not provide because I only have 15 minutes left and I want to skim over a bunch of things. That's unfortunate. Well, so let me give you very briefly a taxonomy of characterization protocols. I'm going to divide them into two halves, the good and the bad. The bad, first of all, is what I would call old school techniques. This is what you learned in graduate school, unless you're currently in graduate school, in which case I have no idea what you're learning. But this is what those of us who went to graduate school around 2000 cut our teeth on. State tomography, process tomography, a bunch of other protocols involving the word tomography. And these methods, I don't want to talk too much about them, involved assumptions that we found out later weren't valid. They basically required pre-calibrated quantum operations in order to learn things about unknown quantum operations. And the trouble is that what we're finding with the devices we have today is that everything is unknown. And so we need self-calibrating methods that do not rely on assumptions that are provably false. These are what I would call modern quantum characterization, verification, and validation. And this is basically the state of play right now. There are two significant families of protocols that fall within this modern category of black box methods that treat the device under test as a black box that has a very limited amount of control, and in particular, that control is purely classical. You get to push classical buttons, you get to view classical outcomes, and you kind of have to cross your fingers and take it on faith that what's going on inside really is quantum. So these fall into two categories that correspond to the two examples I gave on the previous slides. The first is randomized benchmarking and its friends, which Joseph talked about yesterday. The second is gate-set tomography, which you've heard about a couple of times since then, and its variants that are being developed now. Roughly speaking, the randomized methods for benchmarking focus on simplicity. They sacrifice detail. On the other hand, tomography methods, gate-set tomography and its variants, focus on detail and predictive detail, the ability to predict the outcomes of future circuits that you haven't done yet, but that you care about. What they sacrifice is simplicity. So, very briefly, the state of play for randomized benchmarking, I will undoubtedly say something wrong here, so apologies, but fortunately, Joe gave a talk about this yesterday. I think this has become, over the last 10 years, the dominant method for characterizing single qubits, multiple qubits, and the gates on them. It scales pretty well. There are some scaling issues, but it scales pretty well with the number of qubits. You get one number from standard randomized benchmarking. The variants give you a few more numbers, but you typically get order one numbers out. And we believe and or hope that these numbers tell us something important about the device that we're characterizing. The enhanced variants include interleaved randomized benchmarking, unitarity, dihedral benchmarking. These have shown up over the past 5 years or so. The goal here is to probe some more numbers. But one of the themes of this talk that I want to put forth relatively gently is I don't think that those numbers are enough. I think you need a lot of numbers to characterize devices at the scale and at the precision that we want if we're going to invest tens of millions of dollars in scaling them up. You want to know as much as you can, and yes, it's hard, but it's still cheap compared with putting $10 million in the wrong place. And randomized benchmarking is not intended for predictive modeling. It's possible to do so with some effort and with a lot of approximations, but it's really not the purpose of RB. It is the purpose of gate-set tomography. And so the state of play for GST, this is only about 4 years old at this point. This was first proposed by IBM in a PRA by Seth Merkel et al. And since then, Sandia has sort of picked this up and developed the heck out of it. We released a little less than a year ago an open source software package called Pigsty, Python GST implementation, that pretty much solves the problem of providing predictive characterization on 1 and 2 qubit subsets of a quantum information processor. Predictivity is great, but the price is you get higher complexity, a lot higher complexity. This is not something where, as far as we can tell, it's very practical to roll your own software. Dozens of groups have written their own RB analysis it's about 100 lines of Python at most. GST is more like 20,000 lines of Python right now, and I don't recommend rolling your own. This is mitigated by the fact that we put an enormous amount of effort into creating the software to do it, and you can download it off of GitHub. As currently conceptualized, GST does not scale to larger systems. I mean, in principle it could, but it scales with exponential difficulty to larger systems. And this is the big knock against GST. So, if you're an experimentalist and you want to characterize 1 to 2 qubit gates, that's a good idea, because in principle, if you know what your 1 and 2 qubit gates are doing, that's all you need to know. You're done. People build whole circuits. People build Shor's algorithm out of 1 and 2 qubit gates. Of course, in principle, your quantum computer works perfectly. In practice, more is different. When you start putting these things together, weird stuff happens. So I'm not actually trying to tell you that all you need to do is to characterize subsets of 1 and 2 qubits. But right now, what are your options? You have RB, you have GST. They are both, I think, fully ready to use. Which one you use really depends on what you're trying to accomplish. I think they have different purposes, and both of them are part of a toolbox that we're trying to make bigger. If you want a quick and easy error rate, then randomized benchmarking is straightforward. You can do it yourself. You can look at the data and understand exactly what's going on. And if something weird happened, you can probably look at the data and figure out what the weird thing was. It's really nice to have something that can be implemented in 100 lines of computer code and that makes easy sense to everybody. On the other hand, you only get one number. And one of the things that we've realized very recently is that it's actually not clear what that number is. There were some assumptions made or assertions made about what the RB number was measuring that turn out not to be reliable. What I would say is it's not clear at this point. It's one of the things that I hope gets cleared up over the next year or so. RB is clearly measuring something. The question of whether it's measuring a thing that is the right thing for predicting, say, fault tolerance is kind of open. On the other hand, if you want predictive modeling, if you want to be able to predict how circuits are going to behave, or you want to do debugging of your gates, you know that something's wrong with your quantum operations, you just don't know what. You don't know which way it's over-rotating or which field is jiggling. Then GST is a pretty optimized tool for that, and there's a large infrastructure of software support to make it pretty trivial to deploy. So you have two tools. You can use either one of them. Here is as a summary of that discussion, an analogy. If you're in AMO, then you're in the business of detecting photons eventually. There are a couple different ways of detecting photons, and they remain on the market today after decades because both of them are useful. You can go and you can buy a photomultiplier tube, a PMT, and this is unsurpassed for detecting photons. If you want to detect a photon, you want to know whether there's a photon there or not, get a PMT. But all it tells you is there a photon there or not? Maybe you can count photons. It doesn't give you a picture. As ion traps in particular are scaling up, we're seeing ion trappers move from using PMTs to detect photons and make 0-1 measurements on a single ion to using CCD cameras that actually provide a spatially resolved picture of what's going on in a line or an array of ions. One advantage is you can put pretty pictures in your talks. You have a candidate for having a cover of Nature or Science. But more practically, this gives you a lot of information. It's harder. And if you had to build an array of 1,000 by 1,000 photomultiplier tubes yourself, you wouldn't do it. Instead, you go and you buy a CCD camera off the shelf. That's the role that GST is currently playing. It provides, at some additional cost, a very precisely resolved picture of what's going wrong in your quantum computer. Two tools. Hopefully, if I give this talk again in 2 years, we'll have a dozen tools in this toolbox. But right now, we have at least two that appear to be quite reliable. So let me close by talking about where we go from here. We need to go beyond 2-qubit subsystems in isolation. And the reason is, first of all, crosstalk. Secondly, more is different. Thirdly, we're paranoid. There's all kinds of reasons why we don't want to trust that when I hit qubits 1 and 2 with a 2-qubit gate, nothing interesting happens on the rest of the qubits. So how do we do this? I can identify at least 3 ways. One is we only use randomized benchmarking for more than 2 qubits. This has certainly been proposed. It is a viable possibility. I'm not satisfied with it because we get a very small set of numbers and it's not clear what those numbers mean, and it doesn't allow me to do predictive modeling. The second possibility, which my group is working on right now, is to augment GST with related protocols that are targeted at special purposes. For instance, characterizing crosstalk. This is something that, if you're an experimentalist, you can expect to see being deployed within the next 12 months. And I say that with a certain amount of confidence because we already promised the US government that we would do that. So if we don't, we're in a lot of trouble. So you can depend on it. Honest. The third thing we could do is we could try to invent a way to do tomography on 3, 4, 10, 8, 7, 15, 5 qubits. This is something that everybody knows you can't do. You can't do process tomography on 10 qubits. The fun part is, 20 years ago, everybody knew you couldn't build a quantum computer. So we're going to do number 3. This is where I think the really cool developments in the next year or so, I hope, are going to come out in characterization of multi-qubit processors, is full predictive tomography of 3, 4, 10, 17 qubits. So let me close by talking about that. How do you do that? I'm not going to give you a blueprint. I've only got 3 minutes. The key thing, though, is that historically, tomography on n qubits has been associated with writing down a state or process matrix for n qubits. For 10 qubits, that process matrix is a 1,000,000 by 1,000,000 matrix. You can't even write that down, much less figure out what all the numbers are, which is why everybody knows you can't do it. So obviously the solution has to be to cheat, to come up with a different definition of tomography. And the reason that we think we can do this is that probing a quantum information processor with n qubits does not have to mean writing down a full n-qubit process matrix. We actually have a variety of theoretical techniques already for writing down more efficient reduced models that don't let us write down every n-qubit process matrix, but we don't have to because there are extraordinarily compelling physics reasons to think that if you're doing an elementary gate by blasting a laser quickly onto your system, you are not going to get an arbitrary 10-qubit process matrix. If you could, it would be amazing because some of those 10-qubit unitaries are thought to require an enormous amount of computational effort to generate. So this is the way that we intend to cheat, is to use low-weight quantum operations in a fairly clever, sophisticated way as a model for what your gate operations are doing to your 5, 10, or 17 qubit processor without making unjustified assumptions, with testing all the assumptions that we do make, and hoping that those assumptions were foresighted, that they were informed by good physics, and that if this works, we should be able to predict arbitrary circuits that we haven't run yet, including quantum error correction circuits for logical qubits. So that's what I'm excited about. This is where the conclusion slide would be, but I don't want to call it conclusions because we're just getting started. So let me call it the inspiration slide. The really cool thing is you guys are building quantum information processors. And in fact, right now, you are ahead. I and people like me are running as fast as we can just to grab onto your coattails and hopefully give you a boost further down the road to the next generation, those 10 to 100 qubit machines that Will Oliver was talking about earlier. The new generation, if you weren't aware of this, of black box self-calibrating protocols are really what you ought to be using. Please, don't do state tomography, don't do process tomography. Do something that's got the bugs fixed in it that we've developed over the last 5 to 10 years. And stay tuned, because I'm really hoping that a year from now, we can tell you about substantially more powerful protocols that can do holistic predictive characterization of large quantum processors. Thank you. Low weight Lindbladians. I can unpack, we can unpack that, but that's it in a sentence. That is the number of parameters in the model will scale polynomially. We're looking at weight 2 Lindbladians, and the number of parameters scales as approximately 256 times n squared. That's large, but we're dealing with parameter manifolds already in GST that are of that size. The difficulty is in forward simulation. That's not a problem up to 10 to 17 qubits. Once you get to 50 qubits, you can't do forward simulation. The inverse problem is always harder. This is not intended to solve the problem of characterizing generic arbitrary operations on a 100 qubit processor. This is just supposed to get us through the next 5 years.
Maybe there's time for one more question if there is one. And Travis, maybe you could set up.
So the short answer to that is that we're not trying to characterize whole circuits. We're trying to characterize individual gates. If you have a single gate that entangles 8 or 10 qubits, I would say that I have a problem, but so do you, because your gate's not supposed to do that. We're relying on the fact that gates are intended to be local. But it's a two-body. It only entangles pairs. The MS gate is a sum of two-body Hamiltonians. The 5-qubit MS gates that Rainer Blatt is working on are going to be quite a torture test for these methods. It can, but it entangles them in a pairwise fashion. The MS gate is a sum of XX Hamiltonians on the pairs. So that's part of the motivation for weight 2 Lindbladians.
Okay, thanks very much. So the final talk before the group discussion